Dear participants, welcome to lesson number 3 of our course on quantitative and qualitative methods. In this lesson, we will talk about randomness and probability distributions in random variables. We hope that this session will be understandable and useful for everyone. The content. Yes. The content that we are going to develop today relates to the following points. First, we need to talk about what a random variable is. It is true that in the first 2 sessions we had already covered a bit about these concepts, but today we have the opportunity to discuss this a little more. If we have a clear understanding of the concept of a random variable, we could establish what those mathematical models might be that somehow model its probability. We are going to talk about probability functions, and we are going to discuss discrete distributions, continuous probability distributions, and joint probability distributions. Today, we are going to approach and suddenly show some mathematical models that we will have the opportunity to work on in greater detail during the synchronous classes. We are going to talk about statistical independence, and yes, we will conclude with the possible risks and conceptual errors. That's right. But having mentioned this, let's get started. Well, I want you to think about but you understand, for example, by a random variable. A random variable, as this definition mentions, will be denoted by the letter x. The letter x is a random variable, right? Because that random variable is a function that associates a real number with each element of the sample space of a random experiment. For this reason, it is important for us to remember what the sample space is. Remember that the sample space, as we saw in the previous lesson, is made up of all the possible outcomes or events that could exist in a given phenomenon or a specific random experiment. Well, a random variable x is a function that associates a real number with each of the elements that make up that sample space. Therefore, this random variable will be part of the real numbers. The set of possible values that the random variable can take will be called the range or scope of the variable. And that journey of the variable will consist precisely of those in that journey made up of the possible values that this random variable could take, right? So this concept arises because when we select a sample randomly from a given population, we are actually conducting a random experiment. And remember that the random experiment has those characteristics. That is, we don't really know what the outcome is, but we do know not in advance what that set of possible outcomes is that we could obtain from that random experiment. That's right. And any statistical variable that we can establish from that sample will be a random variable. Yes, it is going to be a random variable. Are we going to provide examples, right? For instance, we can take a certain population, like the number of workers in a company, and establish a random sample, correct? Establish. The fact that we establish a sample at random is already a random experiment. And if in that random experiment, which is establishing a sample, we take a measurement, for example, the age or the average income, or the average years of experience that these collaborators may have, that is already a variable. Isn't it? That is already a variable. And it is a random variable because the outcome is defined by chance. And why is it defined randomly? Because it will depend on the sample that has been formed. In other words, no one knows exactly who will be part of that sample. I randomly select 20 people from a set of 1,000, and when I measure, for example, the average age, or when I measure, for example, the average salary, I will obtain a value. But that value would have been slightly different. It would have been a little different if the sample had been made up of other people. For example, I randomly choose 20 people, and it turns out to be 30. But tomorrow I randomly choose again, and it will no longer be 30. It will be 32 or maybe 25. Why? Because each time the selected individuals may be different. And if they are different, value of this variable called average age, for example, or age will be different. That is why it is said to be a random variable. In a certain sense, it depends on chance on that set of, let's say, conditions that humans do not control. Since we do not control them, we are, let's say, attributing them to chance. And since we cannot establish with precision, because there is randomness involved, we cannot accurately determine what the average age Is right. Well, I might be getting ahead of myself here, but we could potentially establish a probability distribution by considering certain characteristics of it, taking into account the sample space and what the possible outcomes of the range of the random variable are. In other words, we could establish what the probability might be that the age is a certain value, or that it falls between a certain age and another age. That is what we will discuss further on. That's right. Well, essentially, as it says there, a random variable is a variable whose values come from the outcome of a random experiment, and therefore it will have an associated specific probability distribution. In conclusion, if I randomly select 20 people, the average age will be random because the individuals have been chosen at random. However, that age may be subject to a probability distribution. That's right. Well, here is another example. Variable X measures the outcome of rolling a die. The roll of a die is an example of a random experiment. The outcome is a random variable. And what is its range? Possible results are 1, 23, 45, right? Very well. And random variables, we will look at some classifications. Random variables can be discrete, and they can be continuous. That will depend on the type of value they could adopt. Discrete variables, when they take isolated values and their ranges are countable, right? And therefore, they are associated with integers. A 2, 3, for example, the number of children, the number of cigarettes a person smokes, the number of courses a person takes or passes. On the other hand, a continuous variable is subject to, let's say, taking values but within an interval. Okay. Its range is not countable. It cannot always be accounted for with integers, but we can place it within a range. For example, weight, for example, height, for example, age, and for example, people can have an age between certain limits, right? You can suddenly have one in so many kilos and so many kilos. In this way, we can have both types. Why is this important, right? Because the statistics we are going to apply will differ depending on whether the variables are discrete or continuous. And let's say that the mathematical modeling of the probability function will also vary depending on whether they are continuous or discrete variables. Even the way we graph them will depend on whether they are discrete or continuous variables. Well, if the mathematical model is different, logically the graphical part is also different because it is a consequence. Well, now we can talk about the various types of discrete probability distributions. The discrete probability distribution refers to the probability distributions that belong to discrete variables. Well, the first thing we are going to talk about is a probability function, right? Well, it is important to understand that a probability function mathematically is a mathematical expression that in some way, given a value of x, can return its probability. Okay, good. The probability function of a discrete random variable x, considering that x is the value using that the random variable could take, is a function that associates each value with its probability. That is to say, we are going to define that function with an f of x. And we need to understand what a probability function means. A probability function is nothing more than a mathematical expression. It is a mathematical function. It is a mathematical expression that, given a value of x, will return its probability in terms of real numbers, right? Ready. And probabilities can be accumulated. But why can they be accumulated? Because this probability function can give us the result of what the probability is that, let's say, the obtained result is greater than or less than a certain amount. For example, what is the probability of rolling a die and getting a number less than or equal to 4? Right? Perhaps. So when we talk about cumulative probability, we are essentially talking about the distribution function, essentially, right? But we need to differentiate. One thing is a probability function, and another thing is a distribution function. The probability function is going to return something to us. You know that a function is a mathematical expression where you input something and it returns something else. I input the value of a random variable, and it will return something about that variable. In the case of a probability function, it is a function that when given the value of x, will return the probability of that value occurring. But a distribution function, it is a cumulative probability function. So let's say a function that gives me the probability of all the accumulated probabilities from a value of x, right? From a value of x. For example, a probability function would give me the probability of getting, say, number 3 if I roll the die. But the distribution function would tell me, for example, what the probability is, say, of getting if I flip a coin 2 or 3 times. What is the probability, let's say, a probability of having, in each of those flips, obtained at least 1 head or 2 heads, for example, right? Yes, there's a little example that we will see now. Okay. The distribution function of a discrete random variable x is a function f. To differentiate between a probability function and a distribution function, the probability function will be denoted as a lowercase f and the distribution function as an uppercase f. And it associates each value of x sub I having one value from 1 to n, for example. Probability variable, that when taking a value less than that is not always less. That's how it is. Well, that is regarding the probabilities of discrete distributions. When we talk about the probabilities of continuous variables, we are referring to a density function. The density function actually ends up being a cumulative probability function, but it is called a density function because being a continuous variable, what is being formed, let's say, is an entire area under a curve. A curve that would be precisely representing a function, let's say, of cumulative probability, right? Cumulative is that y here, this is usually related to integrals, right? With integrals, for example, in a probability function of a normal distribution, what I calculate is the probability that the value is equal to or less than 5, right? Equal to or less than 5. So am I going to calculate the area under the curve y from -infinity to 5, for example, or from a value to 5, for example, right? That's correct. That's why integrals are often used, as we will see in some examples. Well, and probability distribution. Continuous probability distribution, as I mentioned, is this SOS/EOS, this distribution function, allows me to identify what the probability is of obtaining value equal to or less than given value x. Okay. And I can calculate it by finding the area under a curve. And that curve precisely represents the probability function. And here we have the little graphic example, right? Here we have this curve that represents a probability function. Okay. Is this probability function represented by this lowercase f, right? We are going to explain this a little mathematically because here we will use a bit of integral calculus. I had mentioned to you that the probability function is denoted with a lowercase f, and the cumulative function is represented by an uppercase f. What I am going to have is a lowercase f, which is a probability function. It is a probability function of x. Okay, but what happens? This probability function of x allows me, for example, to know what the probability is of obtaining specific value of x. For example, let's suppose that this random variable SOS/EOS represents the probability that a person is 20 years old, for instance, right? That's it. But since they are discrete variables and discrete variables relate to intervals, what could be useful here, for example, is what the probability is that a person is 20 years old or younger. So mathematically, I will graph this probability function using a curve which is the graph of this function. And if what I want to know is the probability that a person is 20 years old or younger, then what I need to do is calculate, considering that the entire area under the curve represents an accumulated probability. I would like to know, for example, what the area is, how much the area that represents that probability measures. from point number 20 backward. So to do that, what I need is to perform an integral. An integral, in this case, will be defined. In this example, I have an integral from a to b, with a and b being the range of ages I want to establish. For example, what is the probability that a person is between 10 and 20 years old? 10 would be the value of a, 20 would be the value of b, and it could be an integral where the integrand is precisely the probability function at 510, and what I will have as a result is exactly the cumulative probability function, which is the uppercase f. That would be the antiderivative of that lowercase f. So how would I calculate that area? Well, using, let's say, the operation of definite integrals, where I will obtain the antiderivative at a, the antiderivative at b, and I would be subtracting them, and from that, I would be finding the area under the curve between points a and b. In other words, we are operating here with definite integrals. Well, to suddenly cover these points, we also have joint probability distributions, right? Joint probability distributions refer to the probability, let's say, of two conditions, in this case y and x, and that joint probability also has a function, which in this case is f of x and y. Okay, it will always be greater than or equal to 0 for all values of x and y. That's right. If x and y are discrete variables, what I am going to do is a double summation of x and y, which, when applied to the entire range of values that x and y can have, would give me a result because it would represent 100% of the total cases. But, for example, if we are talking about variables that are continuous, I will no longer apply summation. Instead, what I will apply are integrals, right? In this case, with two variables, since we are talking about a joint test of x and y, we would be discussing a double integral. If I integrate it from negative infinity to negative infinity in that double integral of xy, I will also have 1% because it represents the summation of all possible cases of the variables of the joint probabilities of x and y. That's how it is. Well, you can also have the marginal distribution. Remember that the marginal distribution contributes, let's say, to the joint probability, the probability of one of the two variables. In the discrete case, I will only have to perform the summation, right? Only the summation, but the summation in y, not the summation in y. In the case of it being discrete of the function xy, which is the joint probability distribution, where it is expressed, the g of x, okay. And what about the probability, which is the probability function of y, which is the summation of the function in x, of the function x, and that's how it is, right? That is for the discrete case. And for the continuous case, we are using a procedure that is practically similar, only involving several summations. We are talking about integrals. And here the participant has to realize that this is logical, right? Because of the nature of discrete distributions, it makes sense to use summations, but in the case of continuous probability distributions that are established in intervals, I have to apply integrals because these are located under a curve that is continuous, right? Let's say that behavior is indeed continuous, right? That's correct. Well, and finally, I have the conditional probability distributions of the random variable y, which is important. And what does that mean, this? Something very similar to what you saw in lesson number 2, right? What could I have? What is the one I could obtain? A function of the probability of y given x, and that probability of y given x would be equal to the joint probability function between the probability function of x, right? As long as the probability function of x is greater than 0 logically, right? Yes. And similarly, what is the conditional distribution of the random variable x given y, or in other words, what is the probability function of x given y? It would be equal to the joint probability function of x and y divided by the probability function of y, as long as the probability function of y is greater than 0. That's right. Well, speaking of which, right, without, let's say, probability functions, we could establish this example, couldn't we? Well, let's assume that x is the random variable that measures the number of heads in the toss of two coins. The probability tree of the probabilistic space could be found in the following way. Here I have one coin and here I have the other coin. Notice that for the first coin, I only have two outcomes, heads and tails. And for each of those outcomes, I have heads and tails of the other coin. In this way, four options will be generated. In the sample space, heads, heads, tails, heads, tails, tails, heads, and tails, tails. Each one has a probability of 25%, and the sum gives me 100%. Okay, that's right. But a probability distribution would be the following: look, notice, say something, and I want you to pay attention to that little box. The first thing I have is a lowercase f of x. And remember that the lowercase f is a probability function, and below what I have is the distribution. So in the first row, I have to consider that if the value of x, let's assume x is the number of heads I could have, what is the probability that the number of heads is 0.25? What is the probability that the number of heads is 1.50? 50%. Is that correct? And why? Because I could have heads, tails, or tails, heads. In other words, I have a 50% probability that the number x, defined as the number of heads, is 50%. And what is the probability of having two heads? 25, because out of the four options, there is only one that is face-to-face. So I have a probability function there. That probability function would be telling me what the probability is for each value of x, when x is 0, when x is 1, and when x is 2, remembering that x represents the number of heads. Okay. But down below, the capital F already gives me a distribution function. For example, what is the probability that the number of heads is 0 to 0? 25%. But what is the probability that, look, what is the probability that the number of heads is up to 1? I mean, it can be 1 or it can be 0. Perfect. So it would be 75%. And what is the probability that the number of heads is up to 2? That is that it is 0, 1, 2. 100%. In other words, there is a 100% probability that number of heads is 0, 1, or 2. There you realize the difference between a probability function and a distribution function. That's right. Well, logically, I could define this graphically in this way. Notice that the first graph corresponds to a probability function, where if x is 0, I had 25%, if x is 1. Probability increased to 50%, and if it is 2, it is 25%. But the other side, like a little staircase, that little staircase represents the distribution function of the number of heads. If it is between 0, on face, it's 25%. But if it is between 1 and, what is it called? And if it is up to 2 faces, that completes the 100%. Indeed, there you have a graph of the probability function alongside a distribution function. That's right, this is a discrete variable. Okay, this is a discrete variable. But then I also have a continuous variable, and I will be able to express the probability function through a mathematical expression. And with this, we are going to close this session, right? For example, here I have that. The probability function will depend. Probability function of x will be 0 if x is less than 0, but it will be e raised to the power of negative x if x is greater than or equal to 0. So this is a density function, right? Where x, by assuming any value, is shaping a function that accumulates through the function e to the power of negative x, right? That's correct. So let's say that here they would be asking me, for example, how it is evident that the function is non-negative. It is only proven by checking that the area under it is, for example. Let's look at the last part. Shall we? Let's calculate the probability that the random variable takes a value between 0 and 2. Oh, nice, right? So how would it be to calculate the probability that the random variable takes on 0 between 0 and 2? Well, keep in mind that this would involve summing all the probabilities of x between 0 and 2. But since it is a continuous variable, those values would be infinite because we would be talking about not like a discrete variable, which would be 0, 1, 2. Here we would be talking about 0 and 50, meaning with decimals. So what we need to do is an integral, right? Well, in order to perform this integral, it will be a definite integral from 0 to 2, where the integrand is precisely the probability function e to the power of negative x at 510, isn't it? Well, what we basically do here is a bit of integral calculus, where we know very well that in order to solve this integral, we are going to find the antiderivative of this function. Let's recall a little bit of that for those who may have forgotten a bit about integral calculus. Here I have an e raised to the power of negative x. Okay, to be able to find its antiderivative, remember that the derivative of an Euler's number raised to a function of x would be equal to the derivative of the function of x that is in the exponent, multiplied by the same expression of e to the function of x, right? So the antiderivative of this e to the negative x would simply be negative e to the negative x. If you differentiate this function minus e to the negative x. If you differentiate it, it will give you exactly the integrand, which is equal to e to the negative x. That's right, slash, you got it. That's how it is. So that's the function. That's the function. Function, let's say, because from the antiderivative, I have the function of, let's say, density, right? Of accumulation, right? It is e to the minus x, and I have to evaluate it at x equal to 0 and at x equal to 2. So s minus e to the negative x, evaluated at 0 and 2, would be negative e raised to the negative 2, right? And Euler raised to the 0. Calculate that, and it gives me 0.86. What does this mean? The probability that x has a value between 0 and 2 would be 86.46%. That's right, Pei. Well, dear colleagues, that would be what we needed to explain in this session. I hope you enjoyed it, that it was understood, and I will see you next time.